Hey everyone, welcome to the next video from chapter 7. So in this video we're just doing examples of solving for eigenvalues and eigenvectors of matrices. So you'll see how it all works out, what you sort of do to get this process down, and can then do it on your own for solving problems in the future. So let's go ahead and jump right on into it. So I want to do this for the following matrix. So example. I'm going to let A be the matrix 5, 2, minus 1, 2. And I want to find eigenvalues and eigenvectors. All right, so let's get started. So how do I go about finding these things? So what I do, the shortcut to this is basically I take the matrix, I subtract r off the diagonal entries, going from top left to bottom right, and then I take the determinant. So I want to look at the determinant of 5 minus r, 2, minus 1, 2 minus r, which comes out to be 5 minus r, 2 minus r, plus 2. So I get r squared minus 7r plus 10 plus 2 is r squared minus 7r plus 12, which factors as r minus 4, r minus 3. So my two eigenvalues are r equals 4 and r equals 3. So what did we do? I took the determinant of this guy with r subtracted off the diagonal, and I got a quadratic polynomial, which I then factored. You could also plug in the quadratic formula. That would work for you too. And then I get two eigenvalues. Now for each of these eigenvalues, I want to look for an eigenvector. So let's start with r equals 4. So what do? I'm going to take my matrix that I took the determinant of and plug in 4. So right up above, we had 5 minus r, 2, minus 1, 2 minus r as our matrix when we took the determinant, right? That's what this was right here. So now I want to plug in r equals 4, multiply it by a vector x1, x2, and then solve that system of equations to be 0. So I want to look at 5 minus 4, 2, minus 1, 2 minus 4, times a vector x1, x2, and I want this to be the 0 vector. So this here, which this turns into then 1, 2, minus 1, minus 2, x1, x2 equals 0. So now let's write out the two linear equations that we get from this that we're trying to solve. So I see x1 plus 2x2 equals 0, and negative x1 minus 2x2 equals 0. And what you'll see right away, and what you should see if you did this correctly, is that this equation here is redundant. It gives me no extra information because if x1 plus 2x2 is 0, then so is negative x1 minus 2x2. They're effectively the same equations and they'll give me no new information. So I can just throw out this equation because it's redundant and just focus on this one here. Now, I only have one equation to satisfy, but I have two unknowns, so I have a free parameter. So what I'm going to do is I'm going to say pick x2 to be 1. Yes, you do just get to pick them. I would not recommend 0. 0 might not be the best idea because if you pick 0, you kill everything and everything goes to 0 and that's bad. So pick x2 to be 1, which means then x1 plus 2 equals 0, so x1 equals negative 2. Okay, what does that tell me? This tells me here, so the vector minus 2, 1 is an eigenvector for A corresponding to eigenvalue 4. Now, it's not the only eigenvector. If I were to pick x2 equals 2, I would get x1 equals minus 4, which gives me another eigenvector. It turns out in this case, all the eigenvectors for eigenvalue 4 are all multiples of each other. All I care about is that I pick one of them. It doesn't matter that I can figure out what all of them are. It doesn't matter. I just need to pick one and have it work, so I can pick x2 to be 1 and we're fine with that. So this gives me an eigenvector for A with eigenvalue 4. So this is all set. Now I want to do the same thing for r equals 3. So again, I had 5 minus r, 2 minus 1, 2 minus r. So now let's plug in r equals 3. That gives me then 2, 2, minus 1, minus 1. x1, x2 equals 0. right? Because if I plug in 3, this becomes a 2. This becomes a 2 here still, minus 1, and this becomes a minus 1 as well. So my equations are 2x1 plus 2x2 equals 0, negative x1 minus x2 equals 0. And again, these are redundant equations because this one's just a multiple of the other one. So I can just throw this guy out because he's redundant. And so then I just have to look at this one here, and this just tells me that x1 plus x2 equals 0. So if I set x2 to be 1, I get x1 equals minus 1, which means, so minus 1, 1 is an eigenvector for A corresponding to eigenvalue 3. Cool. So there I have found eigenvalues and eigenvectors. But now what does this really mean? Let's look at what happens if I apply A to the vector minus 1, 1. Now this is A, not the fancy one. So this is just 5, 2, minus 1, 2, applied to minus 1, 1. Well, in the first row, I get negative 5 plus 2. And in this one, I get 1 plus 2, which means I get minus 3, 3, which is 3 times minus 1, 1. Right, this is where we started with eigenvalues, looking for straight line solutions. We had something like this set up. So what this says is that along the direction minus 1, 1, multiplying by the matrix A just looks like multiplying by a constant. And it turns out this fact is going to be really helpful when we start trying to solve ODEs of systems like this. Because it's multiplying by a constant, we can handle stuff about constant equations from first order linear equations that are constant coefficient and use their solutions to give us a motivation for moving forward from there. All right, so there is your example of finding eigenvectors and eigenvalues for matrices. That should hopefully make things clear as to what you're supposed to do and how you're supposed to solve all this out. If you have questions, please let me know. We talk about it in class as well, how you actually do these and where these are coming from. And then we'll see the importance of all this tomorrow when we start actually trying to solve first order systems using eigenvalues and eigenvectors. All right, so that's it for this video. Thanks all for watching, and I'll see you in the next one.